Hi, and welcome to our presentation. I'm Matt Fabrizi, and today, Team 35, Team No Nonsense, will be presenting our initial design evaluation for an ammonia production plant. I'm here with my team members, Craig Fitzgerald, Andrea Marin, James Gamble, and Mike Ruskowski, and we are from Penn State Chemical Engineering Department and working with Knitline Chemicals, our Penn State chemical group, and let's get started. So this presentation covers the initial design for constructing our ammonia production plant. We're going to cover the design process, economics, and recommendations that we have to continue with the design after our team is finished. And Andrea is going to talk to you a little bit about some background for our plant.
So, Knitline Chemicals is planning to produce an ammonia production plant in Philadelphia. We're going to be hopefully producing ammonia at over 87,000 pounds per hour. We chose Philadelphia as a location for our plant because it's right along the Delaware River, which makes cooling water much cheaper, and cooling water is one of our biggest utility costs. And also because in Pennsylvania is right above the Marcellus Shale, which makes a methane feed much cheaper. Methane has been decreasing in costs the past 10 years. This is mostly due to increased fracking and in fracking technologies. It is now at 4.3 cents per pound. Ammonia has many different uses. The main ones are fertilizer for agriculture, explosives, and different chemicals like cleaning detergents.
So our ammonia production process is divided into 3 phases, each with a different primary product. See, we're going to take our natural gas phase through phase 1 to get a purified natural gas feed, take out some of the toxic components. We're going to take that purified gas feed, make it into purified hydrogen, which is required for the last step. So that's phase 2, and in that last phase, phase 3, we're going to take that purified hydrogen, combine it with nitrogen, and make our ammonia product. Now, we have each of these phases presented here in our block flow diagram. You can see phase 1, where we're purifying the feed, phase 2, where we're synthesizing our hydrogen, and phase 3, where we are synthesizing our ammonia. Now, our natural gas feed is available at 57,151 pounds per hour, and it is mostly methane with a few contaminants mixed in and a few heavier hydrocarbon species. The first phase removes mercury and sulfur, and Andrea is going to talk to you about that.
Mercury and sulfur are incredibly toxic and corrosive to both the equipment and our catalysts. We're going to be heating up our feed and expanding it to the right conditions. Here we're going to be using zinc sulfide to remove the mercury, which we get from the removal of sulfur using zinc oxide. It needs to be less than 1 pp parts per million, and ours is at 0.7 parts per million. So, good.
And with that feed for purification, we're ready to move on to stage 2 that will be accomplished through a series of equilibrium reactions. And the first part of that stage is our steam reformer, which is the kind of meat of producing this hydrogen. Our steam reformer converts the methane and heavier hydrocarbons into H2 and either carbon dioxide or carbon monoxide, which we will later convert and remove from our process. That steam reformer requires a large feed stream of steam as well as the process stream, and we need to take that out in the next step in an H2O purge, because heating and cooling that water in the process stream for the rest of the process is not at all energetically favorable or efficient. So Craig is going to talk to you about our next steps in hydrogen purification.
So at this point in the process, we have quite an abundance of CO2 and nitrogen, and they need to be removed. we're going to use pressure swing adsorbers to remove both of those products. The pressure swing adsorbers work on the basis of pressurization and depressurization to remove, again, carbon dioxide and nitrogen.
To talk about, I guess, purifying and get very pure amounts of our hydrogen through a membrane separator. We have a membrane separator after the PSA for hydrogen to get purified, and this works because across the pressure gradient across the palladium catalyst, which is porous, allows hydrogen to pass through, and since it's such a light component compared to the rest of the components in the mixture, that's what allows us to get highly pure hydrogen, and the retentate is sent back to the water gas shift reactor, which Mike is going to talk to you about.
So once the stream leaves the membrane separator, there's a high concentration of carbon monoxide in there. That is compressed and then sent to the water gas shift reactor, where it's combined with steam in order to have a high conversion of the carbon monoxide into CO2 and H2 gas. This will then be sent to the steam reformer. The water gas shift reactor and the steam reformer are the same pressure in order to kind of reduce cost.
So the third phase of our process is ammonia synthesis. And so the ammonia synthesis happens in the Haber-Bosch reactor from the previously mentioned purified hydrogen and nitrogen, which we purchased from an outside company because we have to have very low amounts of oxygen in the Haber-Bosch reactor because it's hazardous to this environment in the Haber-Bosch reactor because it causes side reactions, as well as oxygen is a main reactant for combustion. So that's why we need to have very pure nitrogen. And the purification after the ammonia synthesis happens through a liquid vapor flash separator. We're using this because ammonia is liquefied under these after it goes through a little bit of expansion and cooling, but hydrogen and nitrogen are still in the gas phase. There's large disparities in the vapor pressures there because the boiling points of nitrogen and hydrogen are in the orders of -3 to 400 degrees Fahrenheit, while the boiling point of ammonia is only -28 degrees Fahrenheit. And so this affords a product that is greater than 99.5% pure ammonia. We produce about over 140,000 pounds per hour, which is over 1.1 billion pounds per year of the product, and we did meet our target and exceed it for the spec of trying to convert 90% of our methane into ammonia. And so safety is definitely paramount in the design of our plant. The first thing that you can do with safety in a lopa onion is what we use to reference is good process design. And so process design, we made changes to our process that would just limit the amount of reactors we needed, as well as using other substitution techniques and moderation techniques to have the plant be more inherently safe. Secondly, the way we run the plant, we use a 5S system just as, I guess, the kind of culture around the plant. So whenever you're working, just make sure to set things in order, shine, standardize, and sustain, and do all that after you sort. And the last phase of safety, which we hope things never come to prevent accidents, is our PPE. So we have certain PPE you have to wear while on the floor in manufacturing plant: a hard hat, eye protection, ear protection, as well as long sleeves. And when you're handling hazardous waste or hazardous products such as ammonia, you have to wear level A protection, which is outlined by the EPA. We also did unit-specific safety analyses. So an example is a Haber-Bosch reactor where you have very high pressure and temperatures over 1,000 and pressures over 2,900. And what we did was said we had to attach a rupture disc, a pressure gauge, and lastly, spring relief valve. So a rupture disc is there for when you need a large venting area. Rupture discs can't measure the pressure, so that's why you have the pressure gauge on there to check the pressure of bursting of the reactor, of the disc. And lastly, the spring load is just there for more relief to the outside. And now I'm going to pass the mic for the second layer of safety, which is controls.
Thank you, James. So going hand in hand with safety controls is process control. We have two types of control: temperature control and pressure control. In bypass control, we have a process heat exchanger, and we split the inlet feed, and we can control the rate of the feed that's split back into the exit stream in order to change the temperature when the temperature control and sensor senses deviance from the set point. We also have direct control, where the exit stream is measured by the temperature control sensor, and then the stream of the cooling water is increased or decreased depending on whether the temperature needs to be increased or decreased. In pressure control, they both work fairly similar. The exit stream is measured. The pressure control sensor senses a deviance, sends a signal to the valve. The valve is increased or decreased depending on whether the pressure needs to be increased or decreased. I'll hand it off to Matt with some alternative studies.
All right, we conducted a few alternative studies just to make sure that we were really having the best process that we could have. We looked at generating our own nitrogen for the plant. We looked at generating a CO2 product as a profitable byproduct, something that we could sell. And we looked at distilling the ammonia feed instead of using the liquid vapor separation. Excuse me. The nitrogen generation had very high energy costs, so we nixed that idea. And the distillation provided us with more pure ammonia, but because the ammonia was already at the purity spec and we were not getting any more profit from selling it, we decided the liquid vapor separation was just okay. Now the CO2 product was something that we would recommend further development on, as it had a probable revenue of $15 million per year extra just by harnessing one of your waste feeds through another pressure swing absorber, which are pretty energy efficient.
So, when looking at our operating costs, we noticed that our utilities and raw materials accounted for over 90% of our total cost. The other small percentage is being made up of byproducts and fixed costs, which are taxes and other similar things. And we operate at about $200 million per year. As far as our capital cost, half of our capital cost was dedicated completely to process equipment. The next most expensive thing being the ammonia storage for our product. And the capital cost will, in the end, cost us about $220 million. So when we look at our utilities breakdown and our raw materials breakdown, we can see that power is accounting for over 75% of our total utility cost, which is due to the high amount of the high compressions of the compressors in our streams. And our raw material, the highest cost is the nitrogen, which is due to the fact that we have a large nitrogen stream going into the Haber-Bosch reactor to make ammonia. The plant operational costs will increase over time due to steady inflation rates. You can see here that over time our fixed costs will increase due to increases in taxes and various inflation rates. The same goes with our SG&A cost as well as our byproduct cost. The cumulative cash flow diagram shows that about in year 3 we start producing product and eventually have a steady increase until we reach our max increase around year 9, where we kind of level off. And as you can see, around year 5 we become profitable, and then we kind of peak off and stop increasing profitability around year 19. This is our after-tax cash flow. As you can see, the amount of money that our plant makes after year 3 increases since we were making a product. Around year 5 we reach our maximum peak. After that our total sales go down, and eventually our after-tax flow decreases. Due to this, it's going to take us about 78 years before our plant becomes profitable. And now I'm going to hand it off to Craig.
Thank you, Mike. So we did sensitivity analysis, and we looked into changing methane and ammonia costs, and we found that there was a cutoff point of 5 cents per pound for methane and 16.7 cents per pound for ammonia, beyond which there is no profitability for the plant. And now I'll hand it off to Matt.
And really, with that being so close to that profitability line, I think that among the other cost evaluations, Team 35's ammonia production plant, we really just need to do some more development on it, or have some large market changes, which could happen with the ammonia trends going up and the methane trends going down. But really, if we have that development, our ammonia production rate is around 1.2 billion pounds per year, which is a large amount of ammonia. That's great. Our capital costs are high at 220 million, but we are building a brand new chemical plant, and that is something that is always going to have a high capital cost. Our operating costs of $195.5 million per year, we feel could significantly be cut by using the recommendations that we will present to you in just a moment. And our CFPO of 78.26 years isn't quite reasonable to continue development on this plant. Our overall revenue from our ammonia production was about $200 million. And so we would be making $5 million per year which is not enough to feasibly pay off that giant capital cost. So looking into the things that we will look into next are some ways that we might counter that and improve upon it. Our PDRI score was 512 for our project, which is getting towards the end of the concept phase and moving in towards that development, but we really feel that we should go back and make it a stronger process overall. So our recommendations to continue with our project will be to investigate improving the reactors and reaction kinetics. Things like temperatures and pressures are very extreme in our reactors. A lot of those temperatures and pressures, if you drop them, would come with a cost of contamination or of unwanted byproducts. But an analysis on that would really yield some better results as to whether we can cut down on our energy costs via that manner and make our plant more profitable. Also using new technology like enzymes to produce the hydrogen. Enzymes are very efficient, they can be very expensive, but as technology increases, it's definitely something we want to keep our eye on. Also the arrangement of reactors, as you see here, we put 2 PFRs in series instead of just the 1 steam reformer. That has a potential to cut down on things like the massive water stream to push that equilibrium, because each reactor will have an increasing conversion as you add them together, and you won't need that giant feed and giant energy cost with heating that to the appropriate temperatures. We also think and recommend that you should investigate ways to better utilize energy throughout the process. Using turbines instead of just expanders would give rise to a great increase in the power exchange between things like the high duty compressors and really hot heated furnaces. And also along the lines of the heated furnace, we think that if you drop those reaction temperatures and utilize more process heat exchange, you'll cut down on a lot of the fuel costs that are associated with heating those large streams, and that's something that would be important to our plant. And finally, we think and recommend that you should investigate profitable byproducts and recycles within the system. We have a nitrogen purge coming out that could possibly be purified to supplement the pure nitrogen going into the Haber-Bosch reactor. We have a CO2, a very large CO2 stream coming out of the pressure swing adsorber, and that would give us that $15 million per year extra, which could push our plant towards being profitable. It would make it more profitable. I'm not sure that it would be the only solution that we need to look into, but in combination it could make a big difference. And finally, the H2S that comes out of the first 2 adsorbers could be possibly made into sulfuric acid, which can be profitable as well. So in conclusion, we would like to thank our mentors for their help and guidance along the way. It's been an adventure, it's been a learning experience, and we want to thank you for that. We'd like to thank Professor McFadden for all the early Monday and Thursday mornings and all the lessons that you've taught us about process design. The team really feels that we've learned a lot in the class. With those recommendations, we leave you and look forward to pursuing the rest of this project with Knit Line Chemicals. Thank you so much.